Okay, so during the first lecture, we talked about the time-independent Schrodinger equation, or you were exposed to it. I said there's a Hamiltonian and a wave function gives you the energy and the wave function back again. I said we would talk about the form of the Hamiltonian, which is the level of theory. And then I also said that we would talk about the form of the wave function, which in these calculations is going to be a linear combination of atomic orbitals. Okay, so our wave function is going to be made up literally of a linear combination of atomic orbitals, okay, which can be represented by this equation here, where we have a summation, we have a bunch of coefficients, and then we have some kind of a form for our atomic orbital. Okay, so we'll have a radial part, and then we'll have an angular part. Okay, because we have S-type orbitals, we have P-type orbitals, we have D-type orbitals. So we have a distance from the atomic center, and then we also have shape, like the S, the P, and the D. If you want to look at more of the orbital shapes, there's a nice web page that goes through different orbitals, lets you visualize them, rotate them, and do things with it. So you might want to visit that site. Okay. So we have two types of orbitals that come to mind that could be used in the calculation, something called a Slater type orbital or a Gaussian type orbital. Now, a Slater type orbital has a radial part and it has an angular part. Okay, and the radial part has an e to the minus this little symbol zeta r. Okay, and this is a very good mathematical representation of the atomic orbitals. So for example, if you had an S-type function, you would see something that would look like this. So here's our wave function for the S-type orbital and the distance from the atomic center. And this is what the wave function would look like. Okay, comes to this very nice cusp and tails off rather quickly. Okay, so this is a Slater type orbital. So you would think for most of these calculations that we would use Slater type orbitals, but instead most quantum codes for molecular systems use Gaussian type orbitals, where you have an e to the minus zeta r squared instead of the e to the minus zeta r. Okay, and zeta is just a parameter that can be changed. R is the distance from the atomic center. Okay, so these are atom-centered functions. Okay. So if we're going to look at what the shape is of this compared to the Slater type orbital, but it doesn't fit as well. The reason that the vast majority of pieces of software utilize Gaussian type orbitals over Slater type orbitals is for computational efficiency. The two electron integrals, which is the heavy duty part of the calculation, can be performed analytically with Gaussian type orbitals. And they can't be done analytically with Slater type orbitals. It has to be done numerically, which has a much higher computational cost, okay, with the grid and the data points. There are a couple of pieces of software out there that do use Slater type orbitals for other reasons, and it becomes very difficult to do frequency calculation and some other intensive calculations with the Slater type orbitals, and you have some numerical issues. So we are going to move forward with Gaussian type orbitals, which is what is implemented in most pieces of software. So with basis set terminology, you'll hear things like, oh, my zetas went away. These should all be zetas. So I will fix that and post a new PDF. My font changed them. Okay, so for anybody who's wondering, they should look like these guys here, the zetas. Okay. All right, so single zeta, by definition, is each atomic orbital is described by one Slater type orbital. That's the strict definition. Double zeta would be 2, triple zeta would be 3. And this is when, you know, calculations were first coming online back in the 70s, I believe it was. And so that was the definition of the single zeta, double zeta, triple zeta. And you will see it in the literature a lot. Single zeta quality, double zeta quality. If you're using GTOs, then it's strictly, you know, each atomic orbital is described by 3 GTOs for a single zeta. Double zeta would be 6, triple zeta would be 9. Okay, so that's the basis of the terminology. In reality, in practice, it's no longer that strict definition. Now it's more along the lines of single zeta quality, double zeta quality, and triple zeta quality, as if you were using, you know, up to 9 GTOs per atomic orbital. Okay, so I just wanted to give you a definition because that's all over the literature, and you should have a basic understanding of what that means. Okay, so we have some very basic functions for the S-type orbital, the P-type orbital, the D, F, okay? And then there's some special type functions. There's something called a polarization function and a diffuse function, okay? If you have a basis set is just the mathematical description that you're using for your calculation for the wave function, okay? If you have a polarization function available for an element, that means that you have a function that has one higher angular momentum than what's occupied, okay? So for example, a D function would be added to carbon atoms, okay? Because a carbon atom has electrons in an S and P-type orbitals, right? So carbon atom usually hybridizes to sp3 or sp2, but at its disposal, it has S and P. The polarization function would be a D function. Okay. For a hydrogen, a polarization function would be a P function because hydrogen has S available to it, as electrons in an S orbital. Okay. So why is this important? If you just have an element, polarization functions are not so important, okay? But once you start making bonds, the polarization functions become important, okay? So this goes to a question that somebody asked about, why do we need to add an empty orbital? It's when you go to do bonding. The bonding allows the orbital to polarize, to have more efficient bonding. So you're adding in a higher energy orbital, but you're providing better bonding. So overall, you get stabilization. So this is a dramatic representation. If you have a hydrogen with an S, you add in a little bit of P orbital to it, and you can get polarization where you get a larger lobe over here, which allows for better bonding, okay? Now this is dramatic. In reality, there's a small amount of the P orbital that's being used, not a large amount, but it does stabilize the bonding. So the polarization orbitals become important for bonding and stabilizing that molecule overall, okay? And this is an example of how it allows for better bonding if you have a P orbital, like for carbon, and then you add in some D orbital, you can get directionality, polarization to get better bonding in the molecule, okay? Okay, so polarization functions, generally these days, you rarely do a calculation without polarization functions unless you have a very, very large molecule and you can't afford to put them on because they usually give you much better results, okay? Especially if you have extended pi systems, if you're looking at transition states, you normally need those polarization functions to get good results. Another type of function is something called a diffuse function. Diffuse functions are functions with a very small exponent. So remember our description, our Gaussian type orbitals have that e to the minus zeta r squared, okay? A diffuse function would have a very small exponent, which means it would tail off very far from the atom center, okay? So this becomes important if you are doing calculations on molecules that have density far from the atomic center. For anions, NMR, excited states, sometimes the diffuse functions are important for getting good results, okay? Sometimes they cause problems. So when it comes to diffuse functions, we often start without them, and then we add them in later to see how much they affect the results. Okay, so this is an overview of the Slater type orbitals compared to the Gaussian type orbitals. So this is a very old basis set, STO3G, compared to the STO. So what we have here is the green one is the Slater type orbital, okay? And the red one is the Gaussian type orbital. And you can see that if you have one STO, it looks very much like a 1s orbital. But if you try to do that with a Gaussian type orbital, it's horrible, right? You don't get the cusp at the atomic center, it tails off at the wrong place. So GTOs, a single GTO cannot really accurately represent a 1s orbital. Okay, so you have to do a linear combination of them. So this is the STO3G, and there's 3 functions that are a linear combination. Okay. So this is the linear combination of the STO3G compared to the STO. So you can see at least now we're getting a better representation far from the atomic center, but we're still not getting a very good representation right at the atomic center where the cusp is. Okay, now STO3G is a really horrible basis set. It's a single zeta basis set. So if we go to a double zeta basis set and you overlay it, you get much better accuracy, right, when comparing with the STO, but you're still missing the cusp. Okay. So basically what this is illustrating is for GTOs, you have to include at least 3 GTOs to represent an STO, but really you need at least 6 GTOs if you want to get anywhere near. That's the double zeta. Okay. And if you want to get accurate at the cusp, then you need to go past your double zeta quality basis set. Okay. So even though we're adding 3 GTOs for just 1 STO, it's still a more efficient calculation to use twice as many or more Gaussian type orbitals than the Slater type orbitals for the frequency calculations and the higher computational cost calculations, which is, again, why most programs use GTOs over STOs. Now, the quality of your basis set, in addition to the level of theory, is very important for the quality of your results and goes to how expensive the calculation is going to be. And I use the word expensive, and when I say a calculation is expensive, that means it's going to require a lot of CPU, might require an extensive amount of memory, might require a lot of disk space, or a lot of time to get to the end result. Okay, so that's what I mean by expensive. Okay, so a fundamental understanding of how many basis functions you have and the type of basis functions, the atomic orbitals that you're going to be using in this linear combination is very, very important. Okay, so we're going to spend a little bit of time on this. So we're going to start with something super small so it's easy and clear to understand. Very rarely will you see in the literature STO3G. Okay, this is not a very common basis set in the literature anymore. Every once in a while, you'll still see it for very large systems. Okay, but most of the time you see something higher. But let's break it down based on this. So remember, in the input file, there was one keyword, GF input. If you have the GF input keyword, it will print out something like this in the log file, which gives you a breakdown of the coefficients and exponents used for the basis set. So this is actually probably a good time to mention this. So most of these basis sets have words that go with them, names, right? So the STO3G basis set, or the 321, or 321G basis set, 631G basis set, CCPVDZ. The names of the basis sets across the different programs are not necessarily exactly the same coefficients and exponents. Okay, so this is really important. The names of the basis sets across different programs. So if you do 631G in one quantum code and do 631G in another quantum code, you're not necessarily using exactly the same basis set. Sometimes they change the coefficients and exponents just a little. Okay, so that's why I always suggest people to put in GF input in their input file so they have an exact record of the coefficients and exponents used. I like to equate it to when you buy a reagent for a reaction, you usually write down the lot number, who you bought it from, things like that, okay, because there can be variations. So it's the same idea. All right, so let's break down this STO3G basis set for the carbon atom. Let's look at what it has in here. So it lists that we have an S-type function, okay, and there's 3 of them. These things here are the exponent, this column, which is why I have all these zetas here. And these are the coefficients. Okay, you'll notice the E here. So there's 0.1, e to the minus 0.716 or 7160, blah, blah, blah. Okay, r squared. Okay. And then it adds on another one. So here's your second coefficient, your second zeta, third coefficient, third zeta. So this is called a contracted basis function. Okay. So if these were completely split out, then you would have this plus that, and the coefficients would be optimized. But these coefficients and these exponents are static throughout the entire calculation. They don't change. They're not what's being optimized. Okay, so I've broken it down here for A, right? You have a linear combination of these three functions from 1 to 3 that are listed here with CA1, CA2, CA3, zeta A1, zeta A2, zeta A3. Okay, so if you plugged them all in, the equation would look like this. But only A out front is being optimized during the calculation. So this big A right here will be changed. It will be updated, okay, as it's optimizing the wave function. All right, so then it also has this SP, and this is unique to the pulpal basis sets. So we have, again, 3 functions that are contracted. Okay, so none of these coefficients are changing, and none of these zetas are changing. The only thing that's changing is this B out here, and this C, D, and E. So we have A as a variable, B, C, D, and E. Okay, and these are our functions inside that represent the atomic orbitals, the S, the P, whatever's available. Okay, now this says S and P. So S, it's just S. There's only one. Okay, but when you have a P function, if you add on a P function, you're adding 3 variables because you have PX, PY, and PZ. So every time you add a P function to, say, a hydrogen, okay, you're adding on 3 variables. Okay. So anytime you have a P function, it's 3 more variables that need to be optimized. So overall, we have 1, 2, 3, 4, 5 variables. Those are our 5 basis functions that are being optimized. And then we have 15 primitives. The primitives go to these guys here. So for a carbon atom, we have 1, 2, 3, right? For the inner S, for the outer S, the 1s and the 2s. We have these 3 here, and then we have for the P functions. Okay, so we have 5 variables to optimize and 15 primitives. This number of basis functions is going to have a substantial effect on the quality of the results and the computational cost. The more basis functions you have, the more variables that have to be optimized, the bigger the matrix is, the more 2 electron integrals. Okay, so this is why it's important to have an understanding of how big is the basis set and how much that's going to affect both the computational cost and the quality of the results. Okay, so let's look at 321G for the carbon atom. This is called a split valence basis set. The split valence is we have our contraction for the core. The core is generally considered up to the noble gas. So for carbon, that would be the 1s orbital. Okay, and then you would have a 2-1 split for the valence space. So that would be the 2s and the 2p. On the periodic table. See, normally I'd be sitting in a room and pointing to a periodic table, but now I've got to figure out how to do a periodic table in Zoom. So I've missed that part. Sorry, but you might want to pull up a periodic table while you're watching this, and that might help clarify what I'm talking about with core and the valence space. Okay. All right, so we have a contraction of 3 for the 1s, and then we have a 2-1 split for the valence space for both the s and the p. So what that means now is for the s orbitals, we have 3 variables, and for the p orbitals, we have 6 variables that need to be optimized for the carbon atom in 321G basis set. Okay, and that's what I have laid out here. Okay, so now we have 9 basis functions that would need to be optimized during the calculation and 15 primitives. Now, as far as the primitives go, they don't have a huge effect on the results until you get to calculate or basis sets that have a huge number of primitives. And then they can increase a little bit. So the main thing that you want to look at is the number of basis functions, because that goes to the number of variables that need to be optimized for the wave function. This is one of the more common basis sets that you will still see in the literature today, which starts with 631G. Okay. For some reason, it has a magic balance of computational cost to quality of results. Not just 631G, they usually have some stuff at the end, but the 631G basis set. So you will still see this heavily used in the literature today. Okay. So this is also split valence. So you have 6 contracted for the core and a 3-1 split for the valence space. Okay. You'll notice that the 321G for the carbon atom has the same number of basis functions as the 631G, because the only difference is that the 631G has a 6-3-1 split, and the 321G has a 3-2-1 split. So there's a difference in the number of primitives, but not in the number of variables. But the 631G gets much better results. Okay. Okay, so we still have 9 basis functions. All right, now we're going to be including in our diffuse and polarization functions. And the way that these are designated might vary a little bit from program to program. This is the way that the Gaussian lists them. So if you want to add a diffuse function to the carbon atom, you would have 631 plus G, and this is pretty common. And what I want to illustrate here is we have our standard 6-3-1 split, which I described on the last slide. And then there's an extra function down here, which is the diffuse function. Okay, the diffuse function is going to add that small exponent. You'll notice here it's 0.04, so it's substantially smaller than the other ones, which means that you tail off substantially from the atomic center. You have a tail that goes far out from the atomic center. Okay, so start slow, tails off wide, far out. But that also means that for the carbon atom, you're adding on 4 more variables. 1 for the S diffuse function and 3 of them for the PX, PY, PZ diffuse function. Okay, so a single diffuse function on carbon adds 4 variables. I think, nope, okay. Now adding on a polarization function. Now this one is unique to Gaussian, 631G D prime. The original 631G basis set, when they developed the polarization functions, they had the same exponent from boron through fluorine, which is not too bad for carbon, nitrogen, and oxygen, but is really bad for boron and fluorine. So what the Gaussian program did was they took the 6311G basis set and used the optimized exponent for the D function from there. Okay, so if you're doing any calculations with boron or fluorine, and you're adding a polarization function, you should always use the D prime if you're using 631G. Okay, so this is a little special here. All right, so let me point out here. Here we have our 631, which is what we've had before, and now we have our polarization function. And for carbon, the polarization function adds a D function, right? Now, D functions start to make things more complicated. You have 4 lobes on them, unless you're doing the DZ squared, but on top of that, you can have pure D or you can have spherical D. In pure D, you have 5 functions: D minus 2, D minus 1, D0, D plus 1, D plus 2, okay? If you put them in Cartesian, you have 6 functions, okay? X, X, Y, Y, Z, Z, X, Z, Y, Z, something, X, Y. Okay, so you end up with 6 new variables. Now this is also very important. If you are not consistent, whether or not you're using pure or spherical functions, you will not have the correct number of functions as you go from reactant to product, or when you go to compare results. You'll be using a slightly different basis set. Okay, so one of the things I always suggest when people are doing calculations is not only do they extract the energies and the results from the calculations, but they also extract the number of basis functions so that they know that they have a balanced basis set across their calculations. Okay, and this is going to go to the energy that we'll talk about on the last slide. Okay, so here we have spherical. So you, by default, get spherical if you put the basis set on the route line. But if you specify it a different way, it will default to pure. Okay, so that's why I say you want to count your basis functions to make sure that you're using a balanced set across your calculations. Okay, so anytime you add a D function, you're going to be adding 5 or 6 more variables to every single atom that you add the D function to. Okay, and those 2 electron integrals, the computations that it's going to have to do to get the properties are more expensive with the higher angular momentum functions. The D orbitals are more expensive than the P's, more expensive than the S, okay? Okay, so let's move up to 6311 plus plus G, D, comma, P, right? So this, again, is very prevalent in the literature still today because of its balance of computational cost and quality of results. So this is split valence, 6 contracted for the core, 3, 1, 1 split for the valence space, adding on what looks like 2 diffuse functions, right? How many people think that means 2 diffuse functions? I mean, that's what I would think if I looked at it. Do you think that's correct? Is it 2 diffuse functions or yes or no? I just want to make sure you're out there. I'm not talking to myself. Yay. Right, I mean, that's what I would think. I would think it's adding on 2 diffuse functions, but in Popal basis set world, what this means is add on a diffuse function to both heavy atoms and light atoms. And in Popal basis set world, heavy atoms are everything except hydrogen, and light atoms are hydrogen. So when you see 2 pluses in this Popal style basis set, that means that you've added on diffuse function to hydrogen and everything else. If you only have 1 plus, it only adds a diffuse function to non-hydrogens. Okay? Okay, and then this terminology here, the G is for Gaussian type function. This means to add on a D function and a P function, heavy and light. Okay. Now this is for molecular hydrogens, so we only have hydrogens, but if you just put P there, it doesn't like it. So you still have to put the D in. It wants the two sections. So you generally have to learn how to bend to the will of whatever was coded. And when it comes to the Popal basis set designation, you usually have to put both in there. Otherwise, it won't understand. Okay, so we have a 3, 1, 1 split here. So this says 6, 3, 1, 1. But here we only have a 3, 1, 1 split. So can anybody tell me why they think there's only a 3, 1, 1 split listed here? I'll give you like 10 seconds, and if anybody's brave, they can put it in the chat. Where's my 6? Where's my contracted 6 functions? So I'm going to go back. Oops. Go back 1 slide. And here are my 6 functions for the carbon atom. So where are my 6 contracted functions? Ah, there's no core for the hydrogen, right? It's all valence space. Excellent. Thank you very much. Okay, so that's why we only have 3, 1, 1 listed here, because there is no core for hydrogen. This is molecular hydrogen. Okay. All right, so we have our 3, 1, 1 split, and then we have our diffuse functions, and then we have our polarization function. Now, if you put GF input, it's going to list it for everything. So I have 2 hydrogen atoms. This is the basis set for hydrogen 1, and this is the basis set for hydrogen 2. Okay, so it will tell me I have 14 basis functions. That means I have 14 variables in the linear combination of atomic orbitals that need to be optimized to optimize the wave function. Okay. 7 of them are on hydrogen 1 and 7 of them are on hydrogen 2. And I have P functions on both, right? And I have a diffuse function. And it also breaks it down by symmetry. So this is a highly symmetric molecule, D infinity H, so it tells me how many I have of each symmetry. Okay, so one of the other outputs that you get in your calculation you'll get the valence space, or you'll get all of them if you put pop equals full, population equals full analysis. It gives you the eigenvectors and eigenvalues. So the eigenvalues are just the orbital energies. The eigenvectors are the linear combination of atomic orbitals that make up the molecular orbital. So for molecular hydrogen, here we have O here, that means occupied. Okay, and it's sigma G in symmetry. And we're not going to go into that for this, but it does designate if you have symmetry, it says what it thinks it is. Okay. And then you have a bunch of coefficients. Now here, these are not principal quantum numbers. This is not the 1s orbital, the 2s orbital, the 3s orbital, and the 4s orbital. This is the first S-type function that's available, the second S-type function, the third, and the fourth. Okay. Now I know they keep going here with 5. This is not the 5px. Okay, so it's just it just numbers them. So don't get confused with the principal quantum numbers. So here we have these larger coefficients in front of these s's, so it's a linear combination of those. And then we have another set of coefficients for an S-type function. They have the same sign. So since they're S functions, they should be in phase, and that's what you have for this bonding orbital for molecular hydrogen. And this is just the contour plot if you cut through the plane. Okay. This is an unoccupied orbital. So it's virtual, V. There are no electrons in this molecular orbital because molecular hydrogen only has 2 electrons, so they're in this highest occupied molecular orbital. And if you come here and you look at the large coefficient, it's using this outer S. Okay, so, and then it has this one, but you'll notice the sign is different, right? This one's positive, this one's negative. So since these are spherical orbitals, we just have this s orbital and this s orbital that are out of phase. And that's why you have a node in the middle. Okay, so if they're out of phase, they annihilate each other. This is a wave function. So if you have waves that are out of phase, they annihilate each other. It's the same idea here. And then again, these are unoccupied. Okay, so this is using more like the 2s where we have a node in the middle now. Okay, so it's the bonding of the 2s that's not occupied by electrons. And this would be the anti-bonding using the 2s orbitals. Okay. And this is just a listing of the coefficients that are being optimized, the A through N that was shown in the equation on the previous slide. Okay, so this is the description of the wave function that is used for these calculations. Okay, so you have a linear combination of atomic orbitals to make up the molecular orbitals. It uses Gaussian type functions to describe the atomic orbitals. Okay, so we have a lot of approximations in not only the Hamiltonian, but also in the wave function, because these are not infinite basis sets, right? It's a truncated series. So with the approximations in the Hamiltonian and the fact that we're using a truncated basis set, we have substantial error in the absolute energies of the calculations. Okay, substantial error in the absolute energy. But the relative energies have a cancellation of errors. And this is where it goes to, it's very important to have your level of theory and the basis set that you use consistent so that you get that cancellation of errors. Okay, okay, so this is just a really awful looking graph, but this is a graph of a singlet and triplet molecular oxygen, the absolute energy with the change in basis set. Okay, so it's at the Hartree-Fock level, it's at Hartree's for the energy, and changing from basis set 631G to some other Poble basis sets. And then there's a basis set called the correlation consistent basis sets. This goes from double zeta, triple zeta, quadruple zeta, pentuple zeta, hextuple zeta, okay? And it's supposed to converge nicely. That's the correlation consistent basis sets. Goal is to converge smoothly to a value. But this is a gigantic basis set. Huge computational costs, very high angular momentum functions. Okay. Okay, so I want you to see that we have a dramatic drop in the absolute energy as you go from this double zeta basis set to one with diffuse and polarization to one with triple zeta to additional polarization functions. Okay, That is a huge change in energy. Because remember, it's 627 kcals per mole per Hartree. Okay, so that's gigantic. This is for the singlet, and this is for the triplet. Okay, so the absolute energy is changing dramatically, but the relative is changing at a much smaller rate. So if you look at the difference in energy between the singlet and the triplet, okay, it's changed quite a bit, right? From here to here to here, but it's not as much as what's going on with the absolute energy. And that's because of the cancellation of error. And if you look at the correlation consistent basis sets, you'll see that the difference really stops changing after triple zeta. Very, very little change in a difference in energy. Okay? And this is because of a cancellation of errors. So these absolute numbers by themselves mean almost nothing. It's the relative energies that are important because you have that cancellation of errors. And you will not get that cancellation of errors if you don't use the same level of theory and basis set when you take differences in energy. Okay, so if I tried to take the difference in energy from this to this, I'm going to get garbage. Right? You have to maintain the same level of theory with the same basis set. Okay? Okay, so one of the things I mentioned in the first set of lectures is the Hamiltonian generally does not include something called relativistic corrections. Okay, and that becomes important for very heavy elements. So if we have very heavy elements, we need to incorporate relativistic corrections in some way. Okay. So to do this, what we're going to do is use something called an effective core potential. So the effective core potentials replace the explicit core electrons with a potential. And that potential is developed with a relativistic Hamiltonian for the most part. Okay, so the relativistic effects, you get a contraction of the core and an expansion of the valence space. And if you try to do all electron calculations for a very heavy element, you're not going to get good results unless you use a relativistic Hamiltonian, which is expensive. Okay, so what we do is we decrease computational cost by not explicitly treating the core electrons and replacing it with this potential that is created, generated with a relativistic Hamiltonian. Okay. One thing that you want to be aware of when you're choosing an effective core potential is how large is the core. Okay, how many electrons are you throwing away explicitly and replacing with this potential? So if we take lead, for example, if you use a large core ECP, lead has 78 electrons in the core and only 4 electrons in the valence space. So the only thing that's going to be treated explicitly that could be used for bonding, okay, or the strong quantum electronic effects would be the 2s and the 2p. This is not something that you would want to use if your lead was reacting with something. Okay, if you just needed the property of the 6s and the 6p, then you could use this. Generally, you want to use something like a smaller core ECP. So there's a couple of them available for lead since it's quite heavy. So this small core ECP would have 68 electrons in the core and 14 in the valence space. So we now would have the 6x, 6p, and the 5d in the valence space. This other small core ECP would have 60 electrons in the core, okay, and 22 in the valence space. So you'd have the 5s, 6s, 5p, 6p, and the 5d available. So this is more desirable for quality results, especially if you're looking at the chemistry of the lead directly. Okay, if you just need it for support structure, like it's on periphery and it's just holding some ligands in place, then that large core ECP may be fine. But if you need the chemistry of the lead, then you want these explicit electrons being treated. Okay. Okay, I mentioned that. There are all electron transition metal basis sets that you can use, especially for the first row transition metals. I do want to note that the 631G star basis set is deficient. Okay, 631G star, by the way, is the same thing as 631G parentheses D. Anyway, that basis set is deficient. It's available. You can apply it to your first row transition metal, but it's not going to give you good results. It's missing an essential P function. So what Gaussian did was they added, all right, just add a plus to include that P function. So when you're talking about the first row transition metals, that actually adds a essential P function. It's not a diffuse function. Okay. So there's lots of little caveats and quirks to a lot of these programs. Okay. There's other all-electron transition metal basis sets. If you get to the second row or third row and you're doing all-electron, you usually have to include some kind of relativistic correction in the Hamiltonian. Okay. And tomorrow, we're going to talk about forms of the Hamiltonian. Okay, there are a lot of basis set resources. If you have a web browser open right now, why don't you go ahead and pull up this basis set exchange. It might be a little slow to pull up, but you can click on an element in there and you can look for basis sets that are available for that one. Okay, there's a long laundry list of them. It'll give you the coefficients and exponents. And with Gaussian, you can plug in and use those coefficients and exponents. That is not true of all codes. Software that uses Slater type orbitals with the numerical calculation that is required for the Slater type orbitals, it usually has to use fitting functions. And you need special fitting functions, so you can't just plug and play your own basis set. But with most GTO codes, you can plug and play your own basis set. So I have a question that says, when do we use Slater type orbitals? So there's a program called Amsterdam Density Functional, ADF, and they use STOs. Some people like to use STOs with the, they have basis sets in there with the fitting functions that handle heavy elements, especially for electronic effects, excitation spectra, things like that. So there's some specialty codes that like the STOs, and they have specialty Hamiltonian and calculations that go with it. That is generally when people are using STOs. 95% of the codes use GTOs. Okay, and here's some other resources for different basis sets. But go ahead and take a look at that basis set exchange. Like I said, there's more basis sets than you probably ever wanted to look at. Okay. All right, so let's just, this is our final topic for the lecture before we go on and do another hands-on session, but we'll take a little bit of a break first. So I know we haven't talked about the form of the Hamiltonian yet, but we did talk about the form of the wave function now. So the mathematical description of the wave function, which we refer to as the basis set. The basis set is the mathematical description of the wave function, the linear combination of atomic orbitals. Okay, so I've mentioned this, but I cannot emphasize this enough. When you're looking at energies, those absolute energies are not accurate, okay, because of the approximations that are made in solving the Schrodinger equation. That's both in the Hamiltonian and in the wave function, because it's an incomplete basis set. Okay. So relative energies can have a good cancellation of errors, but only if you are consistent with your level of theory and basis set. If you have balance between the two things that you're subtracting. Okay? Normally we're looking at reaction chemistry. If you want the overall thermodynamics, you're subtracting the product from the reactant or to the transition state. Whatever you use for the product needs to be the same for the reactant. And your overall reaction has to be balanced. That means you can't lose atoms along the way. All right, so however many atoms you have in the reactant has to be the same as the number and type in the product. So if you're reacting 2 water molecules, you have 2 oxygens and 4 hydrogens in the reactant, you better have 2 oxygens and 4 hydrogens in the product. okay, even if you're going to hydronium and hydroxide, okay? And everything has to be calculated with the same level of theory and the same basis set applied so that you get the cancellation of errors. And that's going to give you reasonable, hopefully accurate energetics for the delta H of reaction, delta G of reaction, and delta E of reaction, okay? So you have to remember to keep it at the same level of theory and the same basis set. And this is why I also suggest to pull out the number of basis functions, because when you subtract the number of basis functions from the product and the reactant, you should come up with 0. And if you don't come up with 0, you have a problem, okay? Because that means something's missing. You're not balanced, okay? Okay, so that's the end of lecture 2. We're going to go ahead and take a 5-minute break. So we will resume at 2:55. And we're going to calculate transition states this afternoon. Okay, let's go ahead and get started with the hands-on session. So if you log back into your video portal and go into day 1, you'll see the HS2 PDF. In addition, you'll want to look at this at some point for reference material, okay, to explain some of what's going on for the transition state. But almost everything you need should be in here. Okay, so let me give you a basic overview of what you're going to be doing in this hands-on session. So we're going to be trying to calculate a transition state. So in the first lecture, I mentioned transition states, and I talked about, here you have a reactant, and then you have a transition state, and then you have a product or intermediate transition state, another intermediate, okay? Minimum, transition state, minimum. And you would like to calculate the first order saddle point, okay? If you want to get the overall reaction energetics, you need to calculate both the transition state and the reactant. And if you want the overall thermodynamics, you need the reactant and the product. Okay. But right now we're going to focus on a method to try to find the transition state. And we're going to do something very simple. Now you've already done a calculation on formaldehyde from the first hands-on session. Okay. What we're going to do is we're going to take that molecule, but we're going to set it up in a different way. We're going to do something called a relaxed potential energy scan. So with the relaxed potential energy scan, I've given you the input file. Okay. Again, if you copy and paste, you're going to have to fix it up, right? Because it's going to put extra characters in there. So be careful with the copying and pasting. So again, you have your percent check line, okay? Remember, you have to replace pound with the number that is your account. So training 98 in my case, yours will be training something else. And we're going to call this capital HS2-scan.chk. And that's where it's going to save the checkpoint file. Okay. We still haven't really talked about the Hamiltonian yet. This is a DFT method. I said we'll talk about that tomorrow. So we have our route line, which tells Gaussian what to do. Our level of theory here is this BP86. And then instead of having a basis set name here, I have GEN, G-E-N, which indicates a general basis set. Okay. And I'm going to do an optimization. I want to optimize the geometry, but I want to do it in a special way. So I'm going to add another keyword, equals mod redund. So I'm going to have a separate section that's going to modify the way that it's going to do the geometry optimization. GF input to print the coefficients and exponents of my basis set, and then pop equals full to print out the eigenvectors and eigenvalues, the energies and description of the molecular orbitals. Blank line, title, blank line, charge multiplicity, right? No charge, and no unpaired electrons. And then I have my elements, carbon, oxygen, hydrogen, hydrogen with my Z matrix. Okay. Now I have changed this a little bit. Here, what I've made sure to do is I have these two distances being slightly different. I believe in the last calculation, we did it in symmetry where I had both of those the same. Now I want them to be slightly different. Okay. So I have B2 and B3 as 0.95 and 0.96. So that's these two bond distances here. And the reason is because I need to break the symmetry. I don't want it to have perfect C2V symmetry. I need it to have CS symmetry because I'm going to be breaking the symmetry when I move the hydrogen. So the goal here is to find the transition state of the hydrogen moving from the carbon to the oxygen. Okay, to find that first order saddle point. And as it moves from the carbon to the oxygen, it's going to break C2V symmetry. So if I try to do a relaxed potential energy scan, starting with perfect C2V symmetry, Gaussian's probably going to get mad. So I'm going to break the symmetry manually. Okay, so I just put different distances there. And then I have an angle of 120, 120, and then the dihedral is D1, which is explained here. Okay. Now here's the important line for what I would like to do, which is the relaxed potential energy scan. This says angle 312. Okay, so here's atom 3, here's atom 1, and here's atom 2. And it's going to change that angle, that A1 angle. Okay, I want to do a scan. I want to take 8 steps, and I want to change that angle by minus 10 degrees for each step. Okay, and that's what's explained here. So it's going to perform this relaxed potential energy scan. It's going to define this angle, the hydrogen, carbon, oxygen angle. The initial value is going to be 120. And then it's going to optimize everything else, all the other distances, all of the other angles, dihedrals, okay? And then it's going to change that angle by 10 degrees. It's going to make it smaller. And then it's going to optimize everything else. And it's going to do that 8 times. So at the end of this calculation, what you'll have is 8 data points. Each one of those data points is going to be an energy. And each one of those energies, the entire molecule will be optimized except the angle. So the angle will be changed and everything else will optimize. So what you should find is that there should be an energy that goes up and then comes back down again. And at the top of that energy curve, you should have a reasonable geometry as a starting guess for an actual transition state calculation. So can somebody tell me why the highest energy point of that relaxed potential energy scan is not the transition state, but should be close to the transition state? Does anybody know why it's not? So I'll give everybody a hint. What are we doing is we're moving that hydrogen. Do we let everything optimize or do we freeze some things? Is everything being completely optimized or have we frozen something? So the angle is not fully optimized. The angle is fixed, right, at each one of those data points. So with a relaxed potential energy scan, the high energy point is not the transition state, but it should be close to the transition state, okay, for this reaction. Okay, so the other thing that I have you do is use a mixed basis set. So the gen keyword right here says come down here and look for a basis set section. And what I have here is carbon and oxygen, and this is just Gaussian saying apply to all of it. I want to use the AUG-CC-PVDZ basis set. And then you need 4 stars. If you use 3, it'll crash. If you use 5, it'll crash. It wants exactly 4 stars. It's very picky. And then for atom 3, I want to use the augmented CC-PVDZ basis set. But for atom 4, I want to use CC-PVDZ. Now I have over here told you why I did that. It's very common if you have a very large system and you're looking at some reaction chemistry that you'll want to use a larger basis set in the section of interest and a smaller basis set further from the section of interest. Now you need to make sure that you don't have a, triple zeta basis set right next to a single zeta basis set on atoms that are right next to each other. That's not going to work, okay? But you can have, triple zeta next to double zeta. You can play around with those settings to decrease your computational costs and increase the quality of your results. So for a molecule this size, you would generally never do that, but I'm illustrating the concept that you can put a slightly larger basis set on the atom of interest. This is the hydrogen that we're going to be moving that's involved in the transition state, and a slightly smaller basis set on the one that is not moving, the one that will be staying in place, okay? Okay, so once you do that, you run that calculation, and when it's done, then you're going to want to open those results with Gauss View. And what you should see when you open results and scan is that energy graph that I mentioned, the energy graph that has it going up and then coming back down. And you'll select the highest energy point, save a new input file, and run an actual transition state calculation, okay? And I've given you some additional redundant coordinates for your run with this D after it. The D means numerically calculate the second derivatives, okay? It gives it additional information. If you don't put additional information, it's going to crash on you. Okay, it either wants you to do a frequency calculation to begin with, or it wants you to give it additional redundant coordinates. The other thing that I have you add is no eigentest. No eigentest will not worry about whether or not it thinks it's in a good starting place, and otherwise it'll crash, okay? And then also increasing the number of cycles that you have for the geometry optimization. When it comes to transition state calculations, it usually takes more cycles to optimize that geometry optimization cyclical process. Okay. So you have to increase the number of cycles for a very small molecule because it generally will only give you a small number of steps to converge. Okay, so that's what this max cycle is, and that's explained down here. So after that, when you run this actual transition state calculation, then you will want to load it with Gauss View and visualize the vibrational mode to make sure that it is what you think it is. And if you're unsure if that vibrational mode is consistent with the hydrogen moving between the carbon and the oxygen, going from the reactant to the product, give me your view only link and I can take a look at it with you, okay? Okay, and then I have where you can calculate the energies, and then I have some optional instructions if you would like to do an IRC calculation, okay? All right, so I am going to leave you to try to perform this, and at about 3:45, I will go through it with everyone. So I'm going to go ahead and stop recording and start trying to do the hands-on session, and let me know if you run into any problems. Okay, there have been a couple of questions about sharing the videos for these sessions. Eventually they will be posted and available for viewing. I don't know how quickly they'll be posted and available for viewing, but I will send up a follow-up email with everyone that has attended in regards to where the videos will become available, okay? Okay, let me go ahead and go over what we did. Maybe. If for some reason your Windows ever stop responding, just close the tab and relaunch. The returning back to its original state is really nice. I mean, you can close the tab. You can even close your entire browser and log back in, and you just click launch again, and it brings you back to your desktop. So as long as it hasn't timed out in the queuing system, it brings you back to where you were before. But if you log out, you will not be able to return. You'll have to relaunch a new desktop. Okay, so I'm going to go ahead and use VI. It's my favorite text editor. You may use NEdit, gedit. So the first thing that we did was set up this scan input file. Now you will notice that I have my percent check line with my full path, okay? And I've used case sensitive everything here, capital D for desktop, capital HS for the checkpoint file. But once I left this percent check line, I was not very strict about case sensitivity. So Gaussian input files are not case sensitive except the percent lines or any line that refers to a file name, because file names and directory names are case sensitive, but the rest of the input file is not. So I have my route line, level of theory, basis set, all that good stuff. Okay. Now the other thing that you might notice is that I didn't put a 0 after my period here for the angle and the dihedral. You have to show that it's a decimal. If you leave the period off, it will crash because it wants a decimal for the angle, but you don't have to have the following zeros. Okay, so same thing here, I just put the decimal. Okay, so that's my scan input file. Let's go ahead and look at, I ran it. Oh, let me go over one. Yes, we have time. I wanted to show you the job file. So I have you using this script that will create a job file for you and submit it to the queuing system. Okay, so it automates the task for you. This is the contents of the job file that QPrep has created. This is just a simple little script, no bells or whistles. On the bigger systems, on the HPRC systems, there's a lot more bells and whistles. If you are on your own system that has Gaussian or you're running some other software, you can write your own little scripts that will generate these job files and submit them to the queuing system. The queuing system is simply everybody needs to get in line. Okay, your job gets put in the queue, you get in the line, and when resources become available, your job runs. But for you to use the queuing system, you have to give the queuing system information. So the stuff up top is the information. Okay, what do I call my job? What do I call certain standard output files, standard error files? Okay, which partition do I want to go into? How much time am I requesting? How many core? How much memory? Okay, how many tasks per node? So each queuing system has its own personality and its own information that it requires. Okay, so this class is not really focused on that, but it's something that you need to be aware of, because if you're going to be doing quantum calculations, chances are you're going to be using a very big system with lots of other users, and you're going to have to use a queuing system. So you'll have to learn how to make a job file. The job file tells the queue what resources you want and any other directives. This changes to a certain directory, sets up what you need to run Gaussian, and then it actually runs Gaussian. Okay, and then there might be some other things after it. So I just wanted to point it out to you that this is what QPrep is doing. It's creating this special job file, and then it gives it to the queuing system. It submits it to the queuing system. Okay, that's its job. All right, gives it to the queuing system. Queuing system starts it when the resources are available, when you're allowed to run. And then you get your log file. So the scan for the log file, most of you noticed, did not normal terminate, it error terminated. Okay. And that's not uncommon for scans. Very common for scans to error terminate because you're pushing the atom into areas that might be unstable, and it might have SCF convergence failures, it might have all sorts of different failures. Okay, so instead of just completely ignoring it, we're going to look at the result. And it says inconsistency expecting 9 geometries, but it has 7 because we got an error termination. Give me just 1 second. Okay. There we go. Okay. So we only have 7 geometry steps instead of the 9 that it was expecting. That was the starting and the 8 steps. But that's okay. Let's go ahead and look at our energy. So the results of the scan. So we have the energy going up, and it hasn't come back down again. So this is where I interrupted and I said, let's live on the wild side and let's just take the highest energy point and assume that it is close to the transition state. So if you look at it, you know, the hydrogen is moving along, and it does look like the curve is flattening, and this does look reasonable. It's like halfway between the carbon and the oxygen. So we're going to run with that. So you take the highest energy point. If you want, you can play this. It'll play it. You can even loop it if you want. How many times? Let's do it 3 times. Okay, so it'll do it 3 times. And you can manually step through it. But you select the high energy point, and this is the geometry that you're going to use for the actual transition state calculation. Okay, so if you right-click and File, Save, you can save this as a new input file. Okay, so we were supposed to save it as ts.com. Okay, so if anybody is curious as to where this GJF comes from, on Windows, COM files are system files. So Gaussian.com files don't get along with the Windows operating system, so they have GJF on Windows. On the Linux systems, generally you use .com. You can call them anything you want, but all of the utilities on Linux generally expect them to be called .com, and on Windows expect them to be called GJF, okay? So we're using .com. All right, so you do this and then you save. Now I've already done this, so I'm gonna call it something else real quick, just so you can see it. Okay, so now I have this new input file which has this geometry that is the high energy point from the scan that I believe is a good representation of the transition state geometry. Okay, so I'm going to come back over here and we're going to take a look at that input file. So that input file is not ready to roll. We have to fix up this input file. We have to make changes to the input file. Okay. So there was a question that somebody ran theirs and they got a downward energy instead of an upward. I am not sure why, but before you leave today, if we have time, I would like to take a look at that. So let me go ahead and walk through this, and hopefully we'll have time and I can take a look. Okay. Okay. So this is the input file that Gauss View saved. Okay. Sorry, that is not the one that Gauss View saved. That is the one that I fixed up. This is the one that I just saved. You can see there's a substantial difference, right? Okay, so my percent check line is fine, but my keyword line is not correct. I need to modify these keywords to match what I gave you in the assignment. Okay, and you need to change the mod redone section, and you need to add in the basis set. But what it did give you is the geometry. These are the Cartesian coordinates. So you have element, X, Y, and Z in angstroms. So this is just its position in space in angstroms. Okay, so we gave it a Z matrix in the first calculation. When you saved it from Gauss View, it saved it with Cartesian coordinates. It doesn't really matter whether you provided a Z matrix or Cartesian coordinates, because Gaussian is going to translate it into internal redundant coordinates. Okay, so whether you give it a Z matrix or Cartesian coordinates is personal preference, or whatever's easier to get your hands on. Okay, does anybody have any questions on that? How many people use PDB files for things? Anybody else? Only one person uses PDB files? What about XYZ files? Okay. Okay, those are just different ways of providing coordinates. PDB files, XYZ files, CIF files, res files. Some are more complicated than others, but they all have some type of coordinates in it that tell you where the atoms are in space. Okay. You just need to be able to get those to give them to Gaussian in a form that it understands. Okay. Okay, so let me show you what the final of this was. All right. So here's what the input file looks like after you modify it. Okay, still the same Cartesian coordinates that I got from Gauss View, which was that high energy point. Okay, but I need now, you know, the TS for the optimization, adding in this no eigentest and the max cycles. And then the first time I ran it, I forgot the FREQ. Did anybody forget the FREQ and couldn't look at the vibrations? It's very common. So you run the optimization, you don't add the FREQ, there's no vibrational modes, and you don't get the frequencies. Okay. Especially because on the homework assignment, it's broken on the next line. So if you go to load the log file with normal termination and you can't view the frequencies, the vibrational modes, it's probably because you forgot the FREQ or you missed it. Okay, so let me go ahead and load up that result. And this is the fully optimized geometry. Okay, now I have no idea if this is a first order saddle point or if this is the transition state that connects the reactant to the product, the formaldehyde to the hydroxy something or another. Okay, so I'm going to come in here and look at the vibrational mode. I want to see the displacement vectors. This is encouraging, right? Because it's looks like the hydrogen is moving back and forth between the two atoms. And then I'll do the start animation. Okay, so it very much looks like it's going from the carbon to the oxygen. Okay, if you have a hard time looking at that, you could do the manual displacement. Okay, and you can also, you know, increase the displacement amplitude after you turn that off, sorry. So I'm gonna do the manual displacement, okay? So that looks very much like the reactant, okay, our formaldehyde. And if we push it the other direction, this looks very much like hydroxycarbene. Now, I will say this distance, it looks short, right? This goes to what I said during the first hands-on session, is when you push it really far from the stationary point, the atom position is less accurate, okay? So since I pushed it really far from the transition state, that's why these distances don't look right, right? But it's definitely reasonable motion of the hydrogen moving from the carbon to the oxygen. Okay. Okay, so that's anytime you're trying to find a transition state, you definitely want to look at the imaginary mode to make sure that it's consistent with connecting the intermediate on either side of the transition state. Okay, and that's how you do that. The other thing that I had to do was pull the energies and then try to calculate the difference in energy with some values that I already gave you. Okay. So I'll leave you to do that on your own time. It should come out to some reasonable number. If you get 1,000 kcals, there's a problem. Okay. Okay. The other thing I wanted to show you as to whether or not we had a full optimization. So I gave you a grep command to do that. The grep commands are really nice. What they do is they search for patterns in a file, and then they give you the lines that match the pattern. So if I grep with a dash capital A3, it's going to find any line that has the pattern that I give it plus 3 additional lines. And I'm going to look for 0 point and my log file. Okay. So this is going to pull out the energies. This first one is the energy at 0K, this one is the enthalpy, and this one is the free energy. Now remember, these are absolute numbers for that transition state. By themselves, they mean nothing. It's only the relative numbers that are going to be important, okay, or reasonably accurate. Okay, so let's also look to make sure we got convergence. So I'm going to grep for 4 lines after converged. Oops. Oh. And it gives me a whole bunch of them. And the reason for this is because it's doing the geometry optimization, right? It's taking those geometry optimization steps. So it's a cyclical process until it reaches convergence. And then it has 2 sections where you have 4 yeses. This is the end of the geometry optimization, and this is the output from the frequency step. Okay, so let's look at that real quick with Molden. And then we're almost done. So if I click on Geom Conver, you'll notice that it goes up in energy. Okay, and this is because we're doing a transition state calculation. It's not necessarily going to go down in energy. It might go up in energy. Okay, and if I click on Movie, it optimizes to the final geometry that I got for the transition state. Okay, so each one of these steps had those no's until it hit all 4 yeses, and this was the last point here. Now I do want to show you one more thing. If you load a scan with Molden, it's going to give you something very different than what you see in Gauss View. And that's because it loads every single geometry step. Okay, so this is the first angle, and then it changes the angle, and then it optimizes, then it changes the angle, then it optimizes, changes the angle, optimizes. In Gauss View, when you load the results of a scan, it only shows you the final point at each one of these steps, and that's why you get a smooth curve, as opposed to what you're seeing in Molden. Both can be beneficial. Okay, I use them both regularly when I'm looking at my transition states and scans. If I could make this window smaller, that would be happy. There we go. Okay, so if I come in here and I click Movie, if I do Next, okay, that's what's happening here, is everything else is optimized, and then it changes angle, optimize. Okay, and this was the step that it finally failed on. Okay. So that's why it looks so different in Molden as opposed to Gauss View. Okay, so that's it for this hands-on session. I will stick around just for a little while if you have any questions or want me to look at anything. Okay. And hopefully I will see everyone tomorrow at 10 a.m. as we start talking about the Hamiltonian, okay, the levels of theory.